Welcome back to the Foundry by Forge College. Today, we're jumping right into interacting with the blockchain in tests. Think of this explainer as strapping on our safety goggles and walking into the mechanical testing lab for your smart contracts. We're going to get our hands dirty. Instead of just deploying code into the void and praying to the crypto gods, we're going to poke, prod, and mathematically prove that our contracts actually work. Knowing how to properly interact with a simulated blockchain right from inside your test suite, man, that is what separates the amateurs from the true Web3 engineers. So let's look at the blueprint and figure out how to make our testing environment just as rock solid as the incredible contracts we're building. Now, in our last explainer, you might remember we tackled balancing CPU and memory, really looking at resource allocation for your physical hardware. Well, bridging right from that, we're applying that exact same rigorous discipline here, but to our simulated on-chain testing environment. Because honestly, an unmanaged, chaotic test suite, it's just as likely to crash and burn as an overloaded web server. If you don't control the flow of time and state in your simulated blockchain, your tests get flaky, they run painstakingly slow, and they become incredibly frustrating. Like, throw your laptop out the window frustrating. So let's bring a little order to the chaos, shall we? Here's the lab manual for today. We've got 4 main things on the agenda. First, the basic write and read mechanism. Second, multi-actor simulations. Third, the master reset switch. And finally, our diagnostic toolkit. Let's kick things off with Section 1, the basic mechanism, write and read. To keep our experiments totally focused today, we're isolating 2 distinct test subjects. On one side, we have counter.sol. This is a super basic state contract that just holds a number and has an increment method to count up by 1. It's basically the hello world of blockchain, just proving we can alter data. On the other side, we're stepping it up a bit with test_token.sol. This one acts like a rudimentary ERC20 token, which is the standard blueprint for custom cryptocurrencies, allowing us to test transferring balances between different users. By keeping these subjects incredibly simple, we can focus entirely on the mechanics of the testing framework itself, without getting lost in all the complex business logic. To interact with these machines, we follow a very specific 4-step core testing loop. 1, we deploy the contract to our local Hardhat network. 2, we push a button, meaning we send a transaction, like calling that increment function. 3, we wait patiently for the mechanical gears to stop turning. And 4, we assert the state, basically checking the dials to make sure the final output matches exactly what we expected. Sounds simple, right? But if you skip even one of these steps, the whole experiment completely falls apart. It's like throwing a cake in the oven and trying to frost it before it's fully baked. You're just going to end up with a huge mess. And that actually brings us to a developer's absolute worst nightmare. Imagine you run your massive test suite on Tuesday, and every single test passes with flying colors. Awesome. But then you run the exact same suite on Wednesday, and it randomly fails. It returns stale, old data. You haven't touched a single line of code. So are there ghosts in the machine? What is going on behind the scenes causing this terrifying flakiness? Well, here's the crucial realization. Your testing code is running on your computer's CPU, which is infinitely faster than a simulated blockchain's block time. Flaky tests almost always happen because an eager scientist didn't wait for the blockchain's gears to finish turning. You fired off the transaction and immediately checked the result before the simulated network actually mined the block and updated the record. It's literally like ordering a pizza on your phone and instantly opening your front door expecting the delivery guy to be standing there. You absolutely must use a wait tx.wait before running your assertions. It's the fundamental difference between asking, "Did you do it?" and "Are you done doing it?" Okay, moving right along to Section 2. Multi-actor simulation, where we look at switching contexts. Real smart contracts aren't just used by the one person who deployed them, right? They're interacted with by hundreds or thousands of people at the exact same time. To simulate that massive user base, we use a concept called signers. A signer is basically a test account provided by the local Hardhat network. It comes preloaded with 10,000 fake Ethereum, which sadly you cannot use to buy a real sports car, and an unlocked private key. Think of that private key as a VIP pass that lets your test script authorize actions on behalf of that specific fake user. Hardhat gives you a massive array of these signers by default. The first one is usually the boss, the deployer, but you can grab the 2nd, 3rd, or 20th signer to represent completely different users interacting with your contract during the experiment. So, how do we actually swap which user is pushing the buttons? We use the contract.connect method. Instead of just calling contract.transfer, which automatically defaults to the deployer, connect signer.transfer explicitly hands the control panel over to a specific user.
It essentially tells the testing framework, hey, run this next transaction as if user number 2 clicked the button. It's just a beautifully elegant way to simulate who is allowed to do what, making sure your permissions and multi-user workflows function perfectly under pressure.
Let's turn to Section 3. It's time to install the most important safety mechanism in our entire testing lab, the factory reset switch. Enter the EVM snapshot. An EVM snapshot acts exactly like a time machine for your simulated blockchain. It's this incredibly handy network helper that captures the precise block state, the exact memory layout, and the token balances at one specific frozen moment in time. And why is this so utterly amazing? Well, deploying complex smart contracts is computationally heavy. It eats up a ton of time. So instead of completely tearing down and redeploying our heavy machinery from scratch for every single test, we just deploy it once, take a snapshot, and then rewind time. We just revert to that exact snapshot right after every test finishes. Because without a reset switch, your experiments are inevitably going to bleed into one another. Say test A transfers 50 tokens. Immediately after, test B runs expecting the user's balance to be 100, but it violently fails because test A already altered the math. That's what we call a polluted test state. It's exactly like trying to conduct a highly sensitive chemistry experiment using dirty beakers left over from the last guy. It will completely ruin your day. Snapshots act like a magical dishwasher, granting you an isolated snapshot state. This gives you a clean, deterministic, perfectly sterile baseline for every single run. Across all the diverse Web3 programs we offer, this is absolutely one of the most critical habits to form. Clean tests mean predictable results. Finally, let's wrap up with Section 4, reading transaction receipts, which is essentially your diagnostic toolkit. Remember when we talked about awaiting a transaction using that tx.wait command earlier? Well, when you do that, it returns something magical, the transaction receipt. Just like a physical receipt from the grocery store tells you what you bought and how much you paid, this digital lab report holds the ultimate truth about what just happened on chain. It shows the core status code, did it succeed or revert? It holds the logs of any events emitted during the run, and it shows the exact gas or digital fuel that got consumed. If your assertions fail, this receipt is the very first place you need to look. In fact, I highly recommend you take a mental screenshot of this specific diagnostic checklist right now, just to avoid those phantom errors in your own Web3 projects. When a test fails, don't panic. Just run through these steps systematically. Number 1, ensure the transaction is actually awaited. Number 2, print and inspect receipt.status. Number 3, validate the receipt.events array to make sure the emitted data matches your expectations. Number 4, double-check your signer context. Did you forget to hand the control panel over using .connect? And number 5, ensure you're using snapshots to isolate your state, proving that a previous test didn't sabotage your current one. But what do you do when the gears jam completely, the transaction aggressively reverts, and the resulting error message in your terminal looks like literal alien gibberish? Because sometimes the receipt alone simply isn't enough to tell you exactly which specific line of your Solidity code caused the massive failure. Well, I'm thrilled you asked, because that is exactly what we're going to dissect in our next lesson. We'll be diving deep into diagnosing failures in Hardhat testing, where we'll learn how to extract those hidden revert reasons, read deeply nested stack traces, and truly debug our smart contracts like seasoned professionals. You absolutely won't want to miss that one. To wrap up, by combining proper transaction awaiting, contextual signers, and pristine snapshot states, your test suites are going to be incredibly fast, wonderfully flakiness-free, and hyper-reliable. Be sure to visit forge.college to dive even deeper into the subject, grab the code snippets from today's explainer, and discover more incredible Web3 learning programs. I'll leave you with this final thought for the day. Are your smart contract tests actually testing the contract's logic, or are they just testing your patience? Clean up your lab, set your snapshots, and I'll see you in the next session.